Then I can finally introduce our first speaker, Dr. Remy Gouw from the University of Louvain in Belgium. He does research on cross-modal perception plasticity, and I know him as a great pioneer in open science. He has a GitHub page, which you should definitely visit, where he showcases all his projects, including the open science tools that he is developing, including the Bit Starter Kit, to learn more about the brain imaging data structure principles and COBIDA's checklist. He will tell you more about this later. We have worked together on this COBIDA's checklist, and I think he's a great visionary when it comes to open science. So today he will start off the symposium by providing introduction, broad overview of open science, and also provide some information that the next speakers will also build further up on. So Remy, very happy that you are here and looking forward to the talk. The floor is all yours.
Thank you, Susie. All right, let's do this. Sharing screen. We good to go. All right. You can see my screen? We're good. All right. All right. So open science, what is it and why do it? Okay. And, checklists were mentioned. So I'm just going to check a couple of things. We've checked that people can hear me. You can see my slides. Good. Oh, yeah. Things that I always forget. Let's turn on the captions so that you can actually just see what I'm saying or hear what I'm saying, even if you turn the sound off. And I might need a pointer. So let's do that as well. I always do that. I always forget. I've just shared the links to my slides, where I put my slide on OSF. So they'll be there soon after the talk. And Susie, do not hesitate to just cut me off if I go over time. I'll be completely fine with this. Okay, open science, what is it? You keep using that word. I don't think it means what you think it means. It's a very typical situation that happens when you start talking about open science, is that we don't agree on what it means, and you end up in a lot of misunderstanding. So my first advice to you is that every time someone just mentions the word open science, or if you want to talk about this, ask them what they mean by it. And what I mean by it. So open science is, for me, it is a community. It's a community of people, but it's not like a single sort of monolithic and completely homogeneous community. And it's definitely not a big happy family where like unicorns ride on rainbows towards the sunset. If you just hang out on open science Twitter for more than 5 minutes, you'll see that it's very easy to pick up a very heated fight, in no time. So the way I see open science usually, or the way I'd like to describe it, is like imagining a big communal tent where there are many entrances. There are many ways you can get into open science. And then you end up having to sort of like share this space and cohabitate with some people that you might like or with whom you share the same values, but not with everyone, right? And there are different ways you can get into it. One of them is through open access. Usually librarians really care a lot about this, and it's the outcome of research. Usually the scientific articles that we publish should be made available for free for everyone, especially the citizens who have, through their taxes, paid for the research itself, right? Another aspect is all the dimensions around equity, diversity, and inclusion. This is not only the fact that sometimes our research just focuses on participants that only come from like Western and rich countries, but it's also the fact that even within the research community and amongst researchers, you have people that tend to only come from a certain type of demographics, right? So those are two examples of like equity, diversity, and inclusions that people in open science care about and try to work on. Then you have all the aspects around open data and open source and open source code. I think other people in this panel, in this session, will be telling you about this. So I will let them do that. And there's something that's been coming a bit more important, I would say, in the world of open science for the past 10 years due to the reproducibility crisis, or so-called reproducibility crisis, is all the aspects around doing open, reproducible research. And that's mostly the way I sort of got into open science. So I'm going to tell you a little bit more about that, but I want to say that there are other ways and there are other dimensions to open science that you could include in there. So this is not a complete list of what open science is, but just I wanted to highlight the multifaceted aspect of what open science, what the word of open science actually entails. Okay, just a couple of things about reproducibility and replicability, because those words are thrown around and rarely defined, and that leads to a whole bunch of misunderstandings. So if you have a given finding and you use a given set of data and a given analysis to find this, if you sort of reuse the same data and the same analysis and you get exactly the same finding, then you say that this finding is actually reproducible. And if you do the same thing on a different data set and you still find the same finding, then you say that this is replicable. So that is one of the ways that those two terms are defined, and that's how I usually understand them, but just sort of you know what I'm talking about here. And another thing that the people who care about reproducibility and replicability tend to sort of usually comes associated with it is the idea around transparency. And I really like this quote by John Kebau and David Donahoe that says, an article about computational result is advertising. It is not scholarship. It can be a bit hard to take when we all care so much about getting our papers out. But what they mean by this is that the actual scholarship is the full software environment, the code and the data that produce the result. So the idea is that we don't only care about the what and the outcome of the research. We also care about how we got there and making sure that people can see this. Right. So these are some of the different dimensions that people got into open science through this reproducibility sort of entrance care about. But there's another thing that I need to highlight, because I think I struggled with this for a little while and people tend to be so focused on those things, is that the fact that something that is reproducible, replicable, and transparent doesn't necessarily mean it's true. I'm going to take some very sort of simple pseudocode example to highlight what I mean by this. Imagine that you have a research project that tries to figure out what is the meaning of the life of the universe and everything, right? And you have this code that will give you the answer, and you give it some data and it gives you a given result, right? And whatever data you give it, it always give you 42 as the meaning of life, the universe, and everything, right? So this is reproducible according to the definition that I'm using from before, right? If you give it different data, it will still give you the same result, right? So this is replicable as well, right? And you can even do that either in MATLAB here or in Python, right? So no matter which type of implementation, this still gives you the same results. This is great. And you put that code on GitHub, this is transparent and everything. It doesn't mean it's true unless you're a big fan of Douglas Adams and he's Hitchhiker's Guide to the Galaxy, but we're getting sidetracked here. So, but that's just the important thing that, all those things are important, but they might still not be enough to sort of lead to sort of what we actually really care about, which is good, getting closer to, understanding the word out there. So what I want to highlight as well is the fact that, to me, open science, on top of being this large community, is also a set of practices. And in this way, there are means to an end, and different people might have different ends, and therefore they might rely on different tools within the open science, I would say, toolbox, I would say. So the idea is that we all sort of want to get to the same goal of producing high quality science, right? This is the end goal. And we have different, I would say, sort of proximal means to get there. And you might want to put the emphasis on some others. For a very long time, people were no, we want to produce new results. And that's the thing that's going to get our stuff published. So we want to always get new results, right? If it's if it's already been shown before, then we know it's harder to get it published, right? And through the whole reproducibility crisis, people were some of the emphasis has been now shifted towards, okay, let's put more, effort around replicability. And then people realize, okay, well, if we want to do this, then we need to also start using different sort of research practices around replication and pre-registration and things like this, right? But the idea is that there are all these other sort of means as well that exist, and we should not completely forget. And for a given study, we tend to put maybe the emphasis on one or maybe a set of those. We cannot cover them all, and you might need to use different practices to get to this end goal of high quality science, but you can do it through different ways. Okay, so this was the very sort of big picture of my understanding of open science, to sort of give you an idea of where I'm coming from with this. Why do it? Well, mostly because of this. or at least that's why I do it. I'll tell you a bit more about this. The idea is that when you start a project, you start from a clean slate. You've got an empty page. Everything is super tidy. You've got like 3 files. And as time goes on, the amount of mess, either physical on your desk or in your lab or on your computer, just increases to the point where you just don't know where things are. And it just turned into this horrible, mess that you don't even want to work with it anymore because you don't know where things are. It becomes really painful to work with this, right? And why do we get there, right? Well, the idea behind this is that, we tend to rush. So haste makes waste. We want to spend time answering our scientific question. We don't want to spend time implementing clean code and data structure, right? And we don't have time for this, right? And so we rush, right? We want the answer to our scientific question because we've got a paper to publish, we've got a PhD to finish, we've got a grant proposal to write, right? And we need those answers so that we can keep on going. And usually what we tell ourselves is that, that's fine. I'll just clean the code right before I submit the paper. And every time I hear this, I go like, hey, yes, I'll just clean my teeth right before the dentist appointment. And, people thinking that this is actually a good way to have like a good dental hygiene in general. And I don't think that's how it works. The reason for this is sort of the idea of technical debt, right? It's like you rush. By rushing, you're literally taking sort of a time loan that your future self will have to pay back. And like with any debt that you pay, you have to pay back with an interest rate. And you're not going to like this interest rate because you're going to have to spend so much more time just like figure out what you did and how you did it later. So why do I do it? Well, I use open science practices to help my closest collaborator, which happens to me myself in 6 months. Wouldn't it be nice if this is you just trying to work on some code and you're like, oh my God, this is horrible, right? Wouldn't it be nice if you could just hop into a time machine and go back and visit your past selves and just tell them that, this is not going to be maintainable in the future. Just like fix this now, right? Well, we don't have a time machine. So one way to do this is to adopt some of those open science practices that help you just, sort of keep things clean on the long term and avoid sort of like friction accumulating in your workflow. A personal example. This is a paper I published in a previous life when we were recording neurons in the brainstem of rats. And this is one of the figures in the paper. I tried to figure out where is sort of like, the data that is just that we used to make that graph. And for just that graph, not the whole data set, like just the data behind this, so I can easily replot this. This is what I find. This is all the data was written on a piece of paper that I took a picture of, and now it lives on a file on one of my hard drives. So not exactly the best way to sort of like either just curate your data on your workflow and share your data with others, right? And just to scare you even more, this is what my log file looks like. This is a mess. Like this was me 10 years ago. I don't know what the colors are for. Everything is in French. So if I want to share this with anyone who doesn't speak French, well, tough luck. Not ideal. How I would get around this now? Well, I would definitely rely on using data standards and trying to have a systematic way to organize things. The way we sort of do it in neuroimaging is by using what's called brain imaging data structure, which is sort of becoming the emerging data standards, the way to organize your data. And all BIDS is about is having a systematic way of naming your files to say where the data is going to be, also related to which type of data it is, whether it's pet data or anatomical data, for example. You have also a systematic way to organize your folders for each type of data, for a given session, for a given subject. And you also have a very systematic way of keeping track of metadata, meaning like information about your data set will live in very specific files, like so most of the time sort of like what's called a JSON file, and the same for information about your data set itself, right? The idea is that each piece of information has a very specific place where it's supposed to go, and if you're looking for that information, you know where to find it. And this BIDS applies for MRI, for MEG and EEG, for PET data, and a lot of like associated data. But because this is a neuroscience meeting, I wanted to highlight two things. that you can extend the BIDS standard, right? If you want your data to sort of be covered by BIDS, you can work on what's called a Biz Extension Proposal. And there are two that are currently underway. One is called is for animal electrophysiology data, and the other one is for microscopy data. And all that development process of the proposals is done in public and in open way on Google Doc, on shared Google Docs, and then on like forums, like on GitHub, for example. And you, if you're interested in this and you want your data to have ways to organize your data, I would suggest just get involved. We want you to sort of like help, design this because you're going to need it for yourself. But by doing this, you also are going to help other people to sort of organize their own data later on. Okay, so the data standard was one of the good things that I wanted to mention. The other aspect is reporting standards. So the idea that if you read a paper, you might just come across a method section that says, yes, devices were fabricated previously as described previously, and it gives you a reference. And then you start going down this rabbit hole of referencing another reference and referencing another reference until you get to a very unsatisfactory answer, but what was actually done, right? And the idea is that a lot of time in neuroimaging, that's especially the case, is that not enough information is shared about how the data was acquired and how it was analyzed. And therefore, anyone wanting to sort of like either reanalyze your data or compare the results to your their results to your own is going to have a very hard time to do that because they don't know what you did. And so that's why a few years back, the Organization for Human Brain Mapping came up with a committee on best practices in data sharing, in data analysis and sharings, or COBIDAS for short. And they came up with reports that sort of there are best practices guidelines on how to sort of like report your methods and report your results and how to share your data. And they are very useful, though I would say that, as Susie mentioned in the intro, they tend to be very long reports. So we're working on making them more user-friendly through like some web-based checklists. But I highly recommend to sort of, if there are standards on how to report methods in your field, try to use those, because it's not only just so that it's going to save other people time, it's going to save yourself time when you want to go back and check what you did later on. Okay, one final point I want to highlight is the fact that in general, and I think maybe the point has come across already, is like increasing standardization in your workflow and everyday sort of work will sort of prevent friction from accumulating in the process, meaning for yourself, but also in general with others when you start collaborating. And I want to just quickly mention this project that several people in this session, several of the speakers in this session were part of, which is called the Neuroimaging Analysis, Replication, and Prediction Study, or NARPS for short. And the paper sort of came out last year. I'm going to give you the quick overview. I'm not going to talk about the results because that's not what I want to focus on here. But just so you understand what I'm talking about, the idea behind the project is that you have an fMRI data set that comprises like the data from 100 subjects. And then you take 7 teams of 200 researchers and you give them the same data set. You also give them 4 months to test 9 specific hypotheses of, we expect to see more activation in this part of the brain under this condition and this condition, right? And that's all you give them. And then you tell them just, go forth and work the way you usually do and give us your answers. And then we compare the results. The idea here was that we want to see how much variability there is when the same data set is analyzed by different people. To see how much variability we should expect, let's say, in the wild when we get some results in the literature. And two of the things that actually made this thing much easier, because anyone who's done a bit of neuroimaging analysis, if you tell them you've got 100 subjects to analyze in 4 months, blood pressure start rising like crazy because you're like, I won't have the time to do this. Well, there are things that make it way easier to do this. Well, one of them, data was shared as a BIDS data set. So there was no need to email the organizers of the study to go like, hey, how is the data organized? No, they just point to one website where everything is described and you know where everything is. The other advantage of BIDS is that because everything is so well structured, you can organize entire pipeline to analyze your data, and they will run on whatever data set as long as it's a valid BIFS data set. And that really speeds up your work and everyone else's work in general. The other aspect that was really crucial to this project is that each team had to report their methods using the Kubernetes standard, meaning that you had to go through a very precise sort of checklist of what you did and how you did it. This is super important when you want to sort of compare results across teams, just to make sure you got all the information about, to compare their process, right? And some of the results, I was talking with some of the people involved in the statistical analysis of this project, and they clearly said, like, without this, we would not have been able to figure out that some of the weird results we got across teams were due to how the people modeled their data, right? Without this would not have been doable. So that's just to sort of summarize, just to show that, using those sort of standards will help you yourself in everyday life, but also tend to have sort of long-term benefits for the community at large. And that's what I really wanted to highlight there. Is like you're helping yourself by adopting those practices, but others can then benefit from you just doing this as well. Okay, and I think I want to end on a note that is about just be kind to yourself. If you're new to open science, go easy on yourself, because it can be confusing. There are many ways to do it. You don't know what is the best way to do it for your own workflow on your own case. And there are so many options that it's easy to get confused, and you might be tempted to just like do everything at once, right? I was like, I want to do all of that, right? And Christopher Beckman came up with this like buffet analogy of open science. Like, don't try to stuff yourself on everything. Select what works for you for this study. And if you're happy and you've mastered this new skill, this new like research practice, maybe come back for another more and try to implement that in your workflow. But don't try everything all at once from the very beginning. Otherwise, this is going to get impossible, and you're just going to get, you're not going to get anywhere. So just be very easy on yourself in general. Okay, I don't know whether I've rushed too much, but on that note, I would like to thank you. And if you have any questions, I'm happy to take them.
Thank you so much, Remy. It's perfectly nice in time. We still have a few minutes left for questions. I will stop recording now so that we have the individual talks, and then people could maybe start asking questions.